When we take a line integral over a vector field, so we have a curve, some curve C, and it's going through this vector field that has vectors going every different direction potentially. And so we're going to be looking at this as our vector field vector. It's going to be our force vector. So this is a vector field where we're using the magnitude of the vectors as a force. And what we're doing is trying to figure out how much work was done over this curve from T1 to T2. And so we're going to use force times distance equals work. That's the definition of work. Our result could be in joules or whatever whatever unit we're using to express the work done. And so force times distance is what this is all about. So if we look at a point here and we think, okay, we're going to take an infinitesimal distance at a point, and at the point we have a field vector, and we also want to look at the unit tangent vector, because that's the direction we want the vectors to be going in if we want to get maximum work done. So we have force times distance, and this is our force vector, but in my illustration it's not going in the same direction. So we need to figure out how much of this force is actually going in this direction, and that's what has to get multiplied by ds. So if we just think about t, and so F is the force field vector, T is the unit tangent vector, and let's look for a second at how to figure out how much of the force of F is going in the direction of T, and we would use the dot product. Okay, let's look at what's going on behind the scenes. So by definition, the dot product is magnitude of F times magnitude of T times cosine of the angle between them. Okay, well, cosine is going to oscillate. Well, first of all, we can disregard this, the unit tangent vector, because it has a magnitude of 1. So now we're really just looking at magnitude of F times cosine of the angle. And if you think about it, cosine is going to oscillate between -1 and 1. And so if it was at -1, our vector would be going completely opposed to this. It would be taking work away. If it were at right angles, then cosine would be 0. So our force is neither helping nor hurting in the direction we want to go. And then if it's 1, that means they're perfectly aligned, and we know that's the behavior of the dot product. So that's why we use the dot product. And then the strategy is going to be to take an integral over C of the force times little pieces of distance. So what we need to do now, we have a conceptual formula, but it's not a useful computational formula. So what we need to do is figure out how to turn it into a nice formula for computation. Let's think how we would take the length of C, and basically we would just use this concept to derive the integral. And I'm sure you've seen the formula if you're watching this. And so a change in arc length would be delta x squared plus delta y squared, and then we could multiply it by delta t over delta t, but then that bottom one can just slide in under here, and of course it would be squared. And now let's just take it straight to the infinitesimals, and we would have x prime of t squared plus y prime of t squared dt. And but I'm going to write the dt down here, because what I want to do now is I want to start with dr ds, and what we really want is dr dt. And so we're going to use this to substitute in a minute here, but right now I'm going to take dr and divide it by dt. So by the chain rule, and now dr dt is just simply our derivative vector. And then ds dt, well, that's this. And if you look at this, this is nothing more than the magnitude of this. So if we just take this and put it in magnitude marks, then we have the derivative vector over its magnitude. So we just have r prime of t over the magnitude of r prime of t, which is nothing more or less than the unit tangent vector. So a vector that at any point it's going to be going off tangent to C. And now the last thing I want to do is let's take this and I'm going to write it as a differential dr equals the vector unit tangent vector times ds. And then the other thing I'm going to do is I'm going to take this, the fact that this equals this, and I'm going to write dr in a different way. And so what we end up with are two different expressions of dr, and I'm going to use these in a minute to do substitutions. Now we're ready to finish this up. I've put the formulas we just derived right here, and we're going to take this and turn it from conceptual to computational. So we're just going to take the integral, and I'm going to go ahead and put the bounds of integration in. And then remember, this is a function that this curve is the input, so r of t. And I put s here just to show kind of the chain rule, but it's really r of t. That's how we're going to express it. And so we have our vector field function. The input is r of t. So that gets us up to here. And this, we've seen that it is equal to this, which is equal to this, which is equal to this. And so we're going to just substitute this for this. And so we're going to dot that vector with this vector, and that's all going to be times dt. And that's it. That is our formula for a line integral over a vector field. Let's finish with a quick example. So we have our vector field function. We have our curve going through the function. We know, here's our formula. We know we need to plug r of t into f. So if I do that, so this needs both x and y to go here. And here it just needs y to be plugged in there. So here I have that. Here we need r prime of t, so we need to take the derivatives of the components, put them here. So now we have that. This next part, all I did was just clean these up a little, so I haven't really done anything on this second line. Now we're ready to dot these things. So we multiply the two first components, that goes here, plus the two second components, that goes here. We no longer have vectors at this point. It's just a polynomial in this case that's getting integrated. So when we do the integrals, we get these. We do from 0 to 1, we get 45 units of work.